Welcome back. Problem 12-15. So this problem is taken from chapter number 12, that is deflection of beams and shaft. And the book name is Mechanics of Material by R.C. Hibbeler. So statement of problem is that two wooden meter sticks are separated at their center by a smooth rigid cylinder having diameter of 50 millimeter. Determine the force F that must be applied at each end in order to just make their end touch. Each stick has a width of 20 millimeter and thickness of 5 millimeter. Modulus of elasticity of this wood stick is 11 gigapascal. So you can see this is a wood stick number 1 and 2 that is separated by a cylindrical, rigid cylindrical body having diameter of 50 millimeter. So its diameter is 50 millimeter. Now when force F is applied, clear, so it will just bend like this. We have to find the magnitude of force F in such a way that we have that there is should be no gap between this. So that is all about this problem. So we have to find this force in order to make their end touch. So let's start with the solution. So first step is that if you focus to only this portion, so this portion acts like a cantilever beam having a point load at its end. So we will just model it. We can model the problem. I will write it. We can model the problem like a cantilever beam. Cantilever. And if we draw it like this, so let this is the cantilever beam having fixed support at this end, a force F is applied, clear, so it force F is applied, so it will deflect like this. Okay, let this is the length X is in this direction, clear, and this is the total length of this beam, which is L, clear. So when you cut it, you can see that here this deflection is half of the radius, which is 25 millimeter. So I will just also write it, the deflection is 25 millimeter. 25 millimeter. So when you cut it at section at anywhere and draw the free body diagram, so it will be like this. This is the beam, there is a force F acts on this beam, and this is the distance X. So when you cut it, you will be having a shear force V and you will having a moment M. Let this is 0.1. So we'll find this shear force and moment by using equation of equilibrium. So sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see F is downward, so minus F plus V is equal to 0. So from here we will get this shear force will be equal to F. Now what we will find is that we will find this moment as well. So sum of all moments about 0.1 is equal to 0 and taking the counterclockwise moment as positive. So about 0.1, one moment is this external reaction moment, which is counterclockwise, it will be positive. Another moment will be F into X, and that is clockwise, so it will be negative. As V is passing through this 0.1, so there will be no moment due to V. So we will write plus M minus F into this distance, which is X, is equal to 0. Okay, this F is also producing counterclockwise movement, so make a correction, this will be also plus. So M plus Fx is equal to 0, so it means that moment is equal to minus F of F into X. What does it mean? It means that we have shown the moment over here is counterclockwise, so from here we get that this moment should be in clockwise direction. So our assumed direction is wrong, so a moment should be in clockwise direction for equilibrium condition. Now we know that We know that from equation of elastic, we have EI into d square v over dx square. This v is small v, which is deflection, or this is not deflection, this is deflection. Yes, this is deflection. So x is equal to moment. Clear? Moment is a function of x. So put the value of moment in this equation, so you will get ei into d square v over dx square will be equal to minus f of f into x. Integrate it once, integrate it, so you will get ei into dv over dx will be equal to minus fx square over 2, and there is a constant of integration which is c1. Let this is equal equation number 1. Again integrate this equation number 1, so you will get ei into v is equal to minus fx cube over 6 plus c1x and plus c2, which is constant of integration. Let this is equation number 2. So c1 and c2 are constant of integration, so we can find them by using boundary condition, using boundary conditions. So what are the boundary conditions? So let's check that. The first boundary condition is that uh, at x is equal to L, we have dv over dx, which is equal to slope is equal to 0. So you can check over here that at x is equal to, x start from here and x is equal to L is this point. So you can see here the slope, which is dv over dx is equal to 0. So what we will do is that we will put in equation number 1. This is the equation of slope. So we will put ei into dv over dx is equal to 0 and x is equal to L. So it will be minus f L square over 2 plus c1. So from here you will get c1 will be equal to fl square over 2. So this is the value of c1. Now we will find c2 by using another equation of boundary condition, and that boundary condition is that at x is equal to L, we have deflection is equal to 0. So again from here you can see that at x is equal to L, we have deflection which is v is equal to 0. So we will put it in equation number 2, which is about deflection. So when you put ei into v is 0 is equal to minus x will be replaced by L. So fl cube over 6 plus c1. c1 is fl square over 2 into x, which is L, plus c2. So 0 is equal to minus fl cube over 6 plus fl cube over 2 plus c2. Okay, so when you take the LCM, so you will be 6 divided by 6 is 1, so minus fl cube plus 3fl cube plus c2 is equal to 0. So we will get 2fl cube over 6 plus c2 is equal to 0. So from here you will get c2 will be equal to minus fl cube over 3. Okay, so you will get this C2. Now we are interested to find out V, and we have, I will choose another color. We have deflection. V is equal to 25 millimeter, which is equal to 0.025 meter. So we will use equation number 2. Put C1 and C2 in equation number 2. So you will get EI into V is equal to minus fx cube over 6 plus C1 is FL square over 2 into x plus C2, and C2 is minus FL cube over 3. And we will get V is equal to, which is deflection, is equal to 1 over EI into minus fx cube over 6 plus FL square x over FLX square over 2 minus FL cube over 3. So if you take out F as common and F over 6 is common, F over 6 EI. So you will get it minus x cube clear plus 3L square into x, and it will be minus 2L cube. Again, when you multiply this with this, so you will get the same. And f into 3FLX L square x over 6i will give you FL square x over 2EI. So you will get this value. Now we have V deflection is given as 0.25 millimeter. Over here you can see this is the deflection V. So you can just put it V is equal to 0.025, as it is as V is downward, so it will be minus. So minus 0.025 will be equal to F over 6 EI into minus x cube plus 3L square x minus 2L cube. And this V is equal to minus 0.025 meter at x is equal to 0. So you can check here that here the x is equal to 0. So we will put all the x 0. So this will be 0 and this will be 0. So we will left with F over 6 EI into minus 2L cube. Okay. So we are interested to find out F. So F will be equal to 6 times EI into minus 0.025 divided by 2 minus 2 into L cube. Now we do not have I, so you can see that we have been given that the width of this wooden is 20 millimeter and thickness is 5 meter. Thickness is 5. So this thickness is 5 millimeter and this width is 20 millimeter. So I will be equal to, for rectangular cross section, I is equal to 1 over 12 BH cube. So 1 over 12, B is 20 millimeter, which is 0.02 meter, and height is 5 millimeter, which is 0.005 cube. And when you calculate it, you will get I will be equal to 0.208 into 10 raised to the power minus 9 meter power 4. Now you have I, you have E, you have L. So you can just put the value 6 multiplied by E is given as 11 gigapascal length of one, this length will be equal to 0.5. Clear? So E is 11 gigapascal. 11 into 10 raised to power 9 multiply by I. I is 0.208 into 10 raised to power minus 9 multiply by minus 0.025 and divide by minus 2 into length is 0.5 cube. So when you calculate it, you will get the value of force comes out to be 1.375 Newton, which is the answer of this question. So it means that when you apply a force of 1.375 Newton here, 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 and here. So these two wooden sticks will meet at this point with there is no deflection, or it will just meet at this end. And that was all about this problem 12-20 12-15. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching my videos and supporting me. Welcome back. Problem 12-31. This problem is taken from chapter 12, that is deflection of beams and shafts, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is the shaft is supported at A by a journal bearing that exert only vertical reaction on the shaft, and at C by a thrust bearing that exert horizontal and vertical reactions on the shaft. Determine the equation of elastic curve. EI is constant. So you can see this is the shaft AB that is supported by a journal bearing at A that only exert a vertical force. Clear? And there is a smooth thrust, there is thrust bearing that exert horizontal as well as vertical forces. So P load is applied at point B, so you have to determine the equation of elastic curve, which means that you have to find the equation of deflection for this beam. So let's start with the solution. We will solve this equation by using discontinuity function, which includes singularity function and Macaulay functions, and you know them very well. So let's start the solution. So if you remove this thrust bearing, so you will be having a reaction force that will be acting upward. Let this force is RC, and you will be having a reaction force as well, which is equal to, this is RCY, and this will be equal to RCX. And if you remove this remove this journal bearing, so you will be having a reaction force which will be acting downward. So we will find these forces by using equation of equilibrium. So sum of first equation of equilibrium is sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see only one horizontal force, which is RC is acting. There is no other force. So it means that RCX will be equal to 0. So this is one reaction force. Now we'll find another reaction force by using equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about this point A, one moment is RCY into perpendicular distance is this one, which is equal to A, and this is producing counterclockwise moment. This will be positive. The second moment that is produced by this force P and perpendicular distance is A plus B, and this is producing clockwise moment, so it will be negative, and their sum must be equal to 0. So I will write RCY into A minus P into A plus B is equal to 0. So it means that we have RCY will be equal to P into A plus B divided by A. This is the value of RCY. Okay. Now we will find this RA. So we will use this equation of equilibrium, that sum of all forces along y direction must be equal to 0 and force upward taken is positive. So RA is downward, so it will be minus RA plus RCY is upward. So plus RCY is P into A plus B divided by A minus this P is downward. Their sum must be equal to 0. So we will get minus RA plus P into A divided by A when you expand it, plus P into B divided by A minus P is equal to 0. So minus RA plus P plus PB over A minus P is equal to 0. So this P and this P will cancel each other. So we will get RA will be equal to PB over A. Now you have all these three reaction forces clear. So we will move toward finding the equation of elastic curve. So we know that EI into d square V over dx square is equal to moment. So here we will use discontinuity function, in which we will find a single equation for moment by using discontinuity function. A single moment function will be generated by using discontinuity function. So we will use singularity function because singularity function only covers the point load and moments. So this is the table that is available in chapter number 12, deflection of beam and shaft. So these are the loading. First column show loading, the second column shows loading function, third is shear, and the fourth one is movement function. Since we are interested in movement and this case shows you only the concentrated force at these points. So what will be the case we will use? So we will use the singularity function, and the case will be this second one. So I will copy this. I have already this one and paste it over here. So we will take the help of this second row of the table and we will calculate the moment function. So starting from here, you can see that P load is applied at this X start from here, clear, and P acts at a distance of A. So in this case, the first load is RA, which is equal to PB over A, and RCY is P into A plus B divided by A. So we'll start from the left hand side and we will move towards the right hand side, and at the right hand side at the end you will neglect this load. Okay, so starting from this point A, so you can see load is PB divided by A, and since here this P is started from this point, this P is starting from this point and it is downward, so its moment function is given as P. First we will write the moment function. So moment function is P into Macaulay's bracket x minus A power 1 for this load. You will also write, as you can see, this load P is upward and this force is downward, so it will be minus P. Now this force RCY, which is P into A plus B, is upward, so I will write another plus P into x minus A power 1. Okay, here this P is equal to, we will write it as RA and this will be equal to RCY. So RA is PB divided by A, and here you can see A is equal to 0. In this case, A is on X. This RA is on X, so A is equal to 0. So I will write X minus 0 power 1 plus RCY, which is equal to P into A plus B divided by A into X minus. Now you can see here this load is acting at this point, and X start from here, and A is this one, so it will be X minus A whole power 1. Okay, so this is your required moment equation. Okay, and this is minus PV. Now you will put this M in here, so you will get EI into d square V over dx square is equal to minus PB over A X clear power 1 plus P into A plus B divided by A into X minus A power 1. So if you further simplify it, you will get EI into d square V over dx square is equal to minus P A into X plus P into A plus B divided by A into Macaulay bracket X minus A. Okay, so this is your equation. Now integrate it, we will get EI into dV over dx is equal to minus PBX square over 2A plus this constant P into A plus B over 2A into X minus A power 2 divided by 2 divided by A divided by 2, and we have left with this A, so this is 2A, and there will be a constant of integration C1. So this is your equation number 1. Again integrate equation 1, we will get EI into V, which is deflection, is equal to minus PB X cube over 6A plus P into A plus B divided by 2A into X minus A power 3 divided by 3. So that will be 6A plus C1X plus C2. So this is your equation number 2. Now C1 and C2 are unknown. C1 and C2 are constant of integration. And they can be found by using boundary condition. So we will write boundary conditions. What are the boundary conditions? So let me discuss this as well. So first boundary condition is that at x is equal to 0, we have deflection is equal to 0. So let me show over here. You can see that here x is equal to 0 and there is a journal bearing. So here deflection will be equal to 0. So we will use put in equation 2, because equation 2 is for deflection. So for x is equal to 0, EI into deflection is 0 will be equal to minus PB into 0 cube divided by 6a plus p into a plus b over 6a into 0 minus a whole cube plus c1 into 0 plus c2. Okay, so this will give us 0 plus, now this term inside the Macaulay bracket will be minus a, so anything inside the Macaulay bracket which is negative will be considered as 0. So this whole term will be equal to 0. So 0 plus c1 into 0 is 0 plus c2, and that is also equal to 0. So from here you can say that c2 is equal to 0. Now second boundary condition is that at x is equal to a, we have deflection is equal to 0. So let me show it to you. So here x is equal to a, you can see x start from here, and at this point x is equal to a, so here there is a bearing, so we have deflection will be 0. So we will put it in equation 2, put it in equation 2, we will get this term ei into v is 0, so this term will be 0, so 0 is equal to minus pb into x is a, so pb a cube over 6a plus this is x minus a, so x is a, so this term will be also 0. Okay, so this whole term will be 0 because x is a minus a is 0. So this whole term will be 0. So 0 plus c1 into x1. So c1 into x is a. So c1 into a plus c2 is again 0. So from here you will get c1 will be equal to plus p b a cube over 6a square. So it will be pb a over 6. So this is the value of c1. Now you have c1 and c2, and we need the equation of elastic curve. So put c1 and c2 in equation number 2. So we will get ei into v is equal to minus pb x cube over 6a plus p into a plus b divided by 6a into x minus a whole cube plus c1, which is pba over 6 x plus c2 is 0. So this will be your required equation. If you further simplify, divide ei on both sides, so you will get v is equal to 1 over ei into minus pb x cube over 6a plus p into a plus b divided by 6a into x minus a whole cube plus pba over 6 into x is required equation of elastic curve, and that is the answer of this question. But before ending this problem, let me explain what will be the deflection. Here we said that deflection v is equal to 0 at x is equal to 0. So you can put x is equal to 0, so this term will be 0. This term will be also 0 because x is equal to 0. So minus a in Macaulay bracket will be also 0, and this x will be 0. So it means that deflection will be 0 at x is equal to 0. Now At x is equal to a, we have already discussed that deflection is 0. So put x is equal to a. So this will be a cube. This term will be 0 because this bracket in Macaulay bracket will be 0. And this will be also a. So you can see plus p, here we will get plus pb a square over 6, and here we have pb a cube over 6a. So a will cancel with this, so we will left with minus pb a square over 6a, and this will cancel with this, so we will having deflection is equal to 0. So by using this equation you can find the deflection in the beam, which will be like this. So at any point you can find the deflection with the help of this method or this equation. And that was all about this problem 12-31. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Also, if you are not familiar with discontinuity function or singularity function, so you can just go on YouTube and write down singularity function explained by Adnan Rasheed, so you will get the lecture for that. Again, if you have any question, you can ask me. Thank you for watching. Welcome back. In this problem, we are going to solve problem 12-32, that is taken from chapter number 12, that deflection of beams and shaft, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is the shaft supports two pulleys, load shown, determine the equation of elastic curve. The bearing at A and B exert only vertical reaction on the shaft. EI is constant. So you can see this is shaft and that is supported by this bearing A and B that exert only vertical force, and this load on the pulleys are shown over here, 60 pounds and 40 pounds. So you have to find the equation of elastic curve, which is basically the equation of deflection for this shaft. So let's start with the solution. So first step is that if you remove this bearing at point B that exert only vertical reaction force, so it will be this reaction force will be RB, and if you remove this bearing at point A, you will be having a reaction force which will be downward. Okay, you can take it in any direction, upward or downward, and from the values you will judge whether you have taken the right direction or wrong. So we will find this RA and RB by using equation of equilibrium. So first equation of equilibrium is sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, this force RA is not producing any movement because it is passing through this point. So first movement will be produced by this force, which is 40 pound, and perpendicular distance is this 20, and this is producing clockwise, so it will be negative. The second movement that is produced by this force RB into perpendicular distance is now 40, and this is producing counterclockwise, so it will be positive. So third movement is 60 into perpendicular distance is 60, and this is producing clockwise, so it will be negative. And the sum of all moment about point A will be equal to 0. So I will write 40, this 40 into perpendicular distance is 20, and this is producing clockwise, so it will be negative. RB into total distance is now 40, 20 plus 20 is 40, so plus RB into 40, because this is producing counterclockwise movement, minus this force which is 60, and perpendicular distance is also 60, and their sum must be equal to 0. So from here minus 800 plus 40 RB minus 3600 is equal to 0. So from here 40 RB is equal to 4400. Okay, so from here you will get RB is equal to, this 0 will be cancelled with this, and this will be equal to 110 pounds. So RB is 110 pounds. So we will find RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA is downward, so minus RA minus 40 plus RB, which is 110 minus 60, is equal to 0. So RA will be equal to 10 pounds. Now you have both RA and RB. So RA is 10 pounds, that is downward, and RB is 110 pounds, that is upward. Okay. Now we are moving toward finding the equation of by using equation of we are finding equation of elastic curve, that is can be obtained by using this formula: EI into d square V over dx square is equal to moment, where V is deflection and x is distance along this axis. Clear? So we will find this moment by using discontinuity function, and in discontinuity function we will use singularity method, because singularity method is only valid for point loads and moments, and from this diagram you can see you have only point loads at various points. Now in book you can see, you can find this is the case of point load. Let me show you. This is the case of point load number 2, and here you can see the point load P is applied at a distance of A, and X start from this point. So we will choose this row number 2. I have cropped it and pasted it on in this problem. You can see over here. So this moment, if there is a point load applied, so the function of moment will be this one, so P into x1. So first at this location you can see the first load at the point where x starts, so A is equal to 0 in this case. So we will having this, the moment function will be equal to P, which is equal to RA, so 10 into x minus 0 power 1. Okay, the second force is acting this one, which is minus. Okay, so this force is downward and this force is upward, so moment is positive, so we will take it minus. So be careful while writing this thing. The second force is also downward, which is 40, and this is acting at a distance of 20 inch from this x. So I will write minus 40 into x minus 20. Clear? The third force that is acting is this one, which is upward, and this force is also upward, and this distance is 40. So we will write it plus 110 into x minus 40 power 1, and we will neglect from the value from the right hand side, because it will give you 0 value. So moment function will be equal to minus 10 into x minus 40 into x minus 20 plus 110 into x minus 40. Now you can put it in this formula, so you will get EI into d square V over dx square is equal to moment, which is minus 10x minus 40 into x minus 20 plus 110 into x minus 40. So integrate it once, integrate it the above equation. So you will get EI into dV over dx is equal to minus 10x square. Okay, minus 10x square over 2 minus 40 into x minus 20 divided by 2 plus 110 into x minus 40 square. This is there is square divided by 2. Okay, So you will, if you further simplify it, you will get EI into dV over dx will be equal to minus 5x square minus 20 into x minus 20 whole square plus 55 into x minus 40 power 2. So if you integrate it, there will be a constant of integration it here as well. So C1. Again integrate this equation, again integrate equation, let this is equation number 1. So you will get EI into V is equal to minus 5x cube over 3 minus 20 into x minus 20 whole cube over 3 plus 55 into x minus 40 whole cube over 3 plus C1x plus C2. And if you further simplify it, you will get EI into V will be equal to minus 1.667 x cube minus 6.667 into x minus 20 whole cube plus 18.33 into x minus 40 whole cube plus C1x plus C2. Let this is your equation number 2. So you can see C1 and C2 are constant unknown constant of integration. So we will find them by using boundary condition. So what are the boundary condition? Let me write it and then I will show you as well. So you can see that first boundary condition is that at x is equal to 0 we have deflection is equal to 0. So here you can see at x is equal to 0 there is a bearing, so deflection will be equal to 0. So we will put in equation number 2. So if this term will be equal to 0 because v is equal to 0, and this term will be also 0 because x is equal to 0. This term will be 0 because x 0 minus 20 in Macaulay bracket 0 minus 20 in Macaulay bracket whole power 3 is 0. Anything inside the Macaulay bracket that is negative will be considered as 0. And this will be also 0. C1 into 0 is 0. So it means that C2 is equal to 0. So you will get C2 is equal to 0. Now we will use another boundary condition, and the second boundary condition is that at x is equal to 40 inch we have deflection is equal to 0. So let me show you. Here you can see that x is equal to 40 inch. This is the x. So here we have deflection is also 0 because this shaft is in bearing. So put in equation 2. So at x this term will be again 0. So 0 is equal to minus 1.667 into 40 cube. Clear? Minus 6.667 into 40 minus 20 whole cube plus 18.33 into 40 minus 40 is 0 whole cube. So this term will be 0 plus C1 into 40 plus C2 which is 0. So from here when you calculate it you will get C1 will be equal to 4000. Now you have C1 and C2. So what we will do is that put C1 and C2 in equation 2 because equation 2 defines the equation of elastic curve. So EI into V is equal to minus 1.667 x cube minus 6.667 into x minus 20 whole cube plus 1.18.33 into x minus 40 whole cube. C1 is 4000, so plus 4000 x, and plus C2 is 0. So this is the equation. So divide EI on both sides, so you will get dV is equal to 1 over EI into minus 1.667 x cube minus 6.667 into x minus 20 whole cube plus 18.33 into x minus 40 whole cube plus 400 x, which is the required equation of elastic curve. And you can use this equation to find out the deflection used to find out the deflection at any length of shaft. So if you need deflection at this point, so you can put the value of x at this point, at any length x. Choose the value of x and put it in this equation, so you will get the deflection. And that was all about this problem 12-32. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also check the description box of the every video. The links of all the chapters are present over there, so you can just go and click on it and you will get all the problems of that chapter. Thank you. Welcome back. Problem 12-33, that is taken from chapter number 12, Deflection of Beams and Shaft, and book name is Mechanics of Material by R.C. Hibbeler. So statement of the problem is determine the equation of elastic curve, the maximum deflection in region BC, and deflection of end A of the shaft. EI is constant. So you can see this is the two shafts. These are the bearings at B and C, and at point A and D where there are two pulleys and the force applied is given as P. So you have to find the equation of elastic curve. It means the equation of deflection, then maximum deflection in region BC, and deflection of end A of this point. So due to this loading, the deflection of the beam will be like this one. Okay, so it will be the deflection of beam. So first step is that if you remove this bearing at point B, so you will be having a reaction force. Let this reaction force is RB, and if you remove this bearing at point C, so you will be having reaction force which is equal to RC. So we will find first this RB and RC by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise movement as positive. So about point B, one moment is this P into perpendicular distance is A, and this is producing counterclockwise, so it will be positive. So I will write it P into A. The second movement is about point B is due to this RC into perpendicular distance is 2A, and this is also counterclockwise, so it will be positive. So plus RC into 2A, and the last moment that is produced by this P into perpendicular distance is 3A, and this is producing clockwise, so it will be negative. So minus P into 3A is equal to 0. So PA plus 2A RC minus 3A P is equal to 0. So we will get minus 2AP plus RC 2 times 2ARC is equal to 0. So from here you will get RC is equal to 2ARC is equal to 2AP. So 2A will cancel, so you will get RC is equal to P. Now you will find RB by using equation of equilibrium, and that equation is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So from here you will get this first P is downward, so minus P plus RB plus RC, which is P minus the last P, is equal to 0. So it means that RB is also equal to P. So we have both RA and RB. Also you can see that this beam, this shaft is symmetrical, the loading is symmetrical about this axis. So you can see this P will be equal to this RB, and similarly this RC will be equal to P. So you can do it as well. Now we have this RB and RC, so we know that equation of slope and deflection can be found by using this formula EI into d square V over dx square is equal to moment. So here we will use the discontinuity function, which is singularity function, because the load is point load, and for point load we define the singularity function. So I will write it singularity function for this load. And what is that for moment? So again this equation moment will be equal to, you can see this is the point loading. So if we go to the book and we can check the second scenario, that is for point load. So for if point load P is act at a distance of A and X start from this side, so moment equation will be this one, M into P into X minus A. So note down this. Okay, so we have the equation which was M is equal to P into X minus P into Macaulay bracket into X minus A power 1. Now here for this loading you can see that load is P and A is equal to 0 because X start from here. So we will write P into X power 1 because A is equal to 0. And you can also check that loading is upward, so this value will be positive. Okay, so here the loading is downward, so this value will be negative. The second thing, plus this loading is upward, which is positive, and RB is equal to P. So P into this distance is X start from here. So this is A. So P into X minus A power 1. The third loading is also plus RC, and this will be also plus RC is equal to P into X minus, now distance is A plus 2A, which is 3A. So X minus 3A power 1. And we will neglect the last one. Okay, so this is your moment equation. So if you further simplify it, you will get moment is equal to minus P into X plus P into X minus A plus P into X minus 3A. Now you can put this equation over here. So we will get EI into d square V over dx square is equal to this moment, which is minus P into X plus P into X minus A plus P into X minus 3A. Okay, so integrate it first. you will get EI into dv over dx will be equal to minus px square over 2 plus p into x minus a power 2 divided by 2 plus p into x minus 3a square divided by 2, and there will be a constant of integration which will be c1. Let this is equal your equation number 1. So integrate, again integrate equation 1, so you will get ei into v is equal to minus px cube over 6 plus p into x minus a cube over 6 plus p into x minus 3a cube over 6 plus c1x plus c2. This is your equation number 2. Now you can see c1 and c2 are unknown constant of integration. So we will find c1 and c2 by using boundary condition. Boundary conditions. So what are the boundary conditions? So first boundary condition is that at x is equal to 2a, we have dv over dx is equal to 0. So let me show you here. Now you can see this is the midpoint. Clear? The length is 2a, and here you can see the, if you take tangent to this curve, so here at this point dv over dx which is equal to slope is equal to 0. So put in equation number 1 because equation number 1 is for slope. So if you put dv over, we will choose this equation, we will put this equation. So what we will get is ei into dv over dx is 0 is equal to minus p into a, x will be replaced by 2a. So 2a square over 2. Now here plus p into x 2a minus a power square divided by 6 plus p into 2a minus 3a power square plus c1. Okay, so here you will get minus p into 4a square over 2. Clear? And from this term you will get p into a square over 6, and this term will give you 0 because this will be minus a, so anything inside the Macaulay bracket is negative, it will be considered to 0. So plus 0 plus c1. Okay, so if you further simplify it, so from here you will get c1 will be equal to p plus p 4p a square over 2 minus p a square over 6. Okay, not 6 because this is 2. Okay, this is 2. You can check it, this is 2. So c1 you will get c1 will be equal to, if you take LCM, so p 4p a square minus p a square, so c1 will be equal to 3p a square over 2. This is the value of c1. Now another boundary condition is that at x is equal to a, we have deflection is equal to 0. So let me show you. You can see this is x is equal to a, so here you can see deflection is equal to 0 because this is bearing support. So put in equation number 2 because equation number 2 is for deflection. So ei into v which is equal to 0 is equal to minus p, x will be replaced with a, so p a cube over 6 plus P into A minus A will be 0 plus P into A minus 3A whole cube over 6 plus C1 is 3PA square over 2 into X will be replaced with A plus C2. So 0 is equal to minus PA cube over 6. This term will be 0. This term will be 0 because anything inside Macaulay bracket is negative will be considered as 0. Plus 3PA cube over 2 plus C2. And when you simplify it, you will get C2 will be equal to 4PA cube over 3. Now you have C1 and C2, and we have been asked in first part determine the equation of elastic curve. So put C1 and C2 in equation number 2. So what we will get is that EI into V is equal to minus PX cube over 6 plus P into X minus A power cube divided by 6 plus P into X minus 3A whole cube over 6 plus C1, which is 3P A square over 2 into X plus C2 is 4P A cube over 3. And if you further simplify it, you can divide it by EI on both sides. So you will get V will be equal to 1 over EI into minus px cube over 6 plus p into x minus a power cube divided by 6 plus 3 into p into x minus 3a whole cube over 6 plus 3pa square over 2 into x plus 4pa cube over 3. And if you take p over 6 as common, so p over 6 ei, p over 6 is taken as common, so you will get minus x cube plus x minus a whole cube plus x minus 3a whole cube plus 9a square x plus minus plus if you take as common, so this term is correct, plus 9a square x and so 8a cube. And one thing is that this C2, let me check it, C2 will be equal to, here when you calculate it will be minus 4pa cube over 3. How? So let me check it. You can see that if we take C2 plus LCM, which is 6, so 6 divided by 6 is 1, so minus PA cube plus 3, 2, 6 divided by 2 is 3, 9 PA cube is equal to 0. So C2 is equal to C2 plus, this will be 8PA cube over 6 is equal to 0. So again, 2 4s are 8, 2 3s are 6. So this is minus 4 over 3. So correct it. This value is negative. Again, this value is negative. And this is minus a cube. So this is required equation of elastic curve, which is the first part. Now if we copy this equation and paste it on next page. So this will be the required equation. Okay. So this is 9a square x. This 2 is from the other one. Okay. Now in second part, it is being asked to find the maximum deflection in region BC. So at BC, it means that x is equal to 2a. Sorry. X is equal to 2a. So we will put here at x is equal to 2a, we have deflection will be in region BC, that is maximum deflection, and that is P over 6 EI minus x is 2a, so 2a whole cube plus we have Macaulay bracket, so 2a minus a whole cube plus 2a minus 3a whole cube plus 9a square into 2a minus 8a cube. So we will get P over 6ei, and this will be minus 8a cube plus a cube plus this term will be equal to 0 because minus a in Macaulay bracket will be 0 plus 9 18, 9 twos are 18, so 18a cube minus 8a cube. So minus 8 is minus 16, so I will write it minus 16a cube plus 19a cube, which is equal to P over 6 EI, which is equal to 3a cube. So you will get 3pa cube over 6 EI, and that will be pa cube over 2 EI, and this value is positive, so it means deflection is upward. So deflection in region BC, which is maximum deflection, is this one. Now the third is to find the deflection at A, deflection at point A. So you can see here that here x is equal to 0. So put x is equal to 0 in above equation of elastic curve, which is this one. So you will have deflection at point A will be equal to P over EI. This term will be 0 because x is equal to 0. This will be also 0 because minus a in Macaulay bracket is 0. This will be 0. This will be 0, and we will left with minus 8 over a cube. So we will left with minus 8a cube, and there is 6. So minus 8pa cube over 6ei, and that will be equal to minus 4 over 3 pa cube over ei, and this value is negative, so deflection at point A will be equal to 4 over 3 pa cube over ei, and we will write down downward. Negative means that deflection is downward. So this is the answer of our third part. So what we have, this was the second part. So in first part we have find out the equation of elastic curve. Then in second part we have the find deflection in region BC, which is PA cube over 2EI, and in third part deflection at point A is 4PA cube over 3EI. And that was all about this problem 12-33 by using discontinuity function or singularity function. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.